Okay, so our midterm date is April 11th, 14:30 to our exam. Okay, 16:30. If I do that, are there any conflicts with the other classes? Oh, this one is 16. That's not good. Anybody is taking this course? You are taking it, you are taking it, you are taking it. So we are going to start our exam then at 13:30, and it will be between 13:30 to 15:30. So you will have half an hour of break between two exams. Okay? So this is our midterm exam. Anybody, any conflicts with this exam time and date? Because I am just yes.
Is it conflicting with operating systems midterm?
It will start at 16. Okay, and it will continue until midnight. I don't know. Okay, so you will have half an hour in between. Or if you think that this is, I mean, how many people are taking that course again? 1, 2, 3, 4, 5? Many people? I mean, if you like, I can delay this exam one more week, or maybe I can do the exam next week. Which one?
Delay.
Okay, maybe let's look at this. Our options. I can do exam today, 28th, or I can do it 4th, or 11th, or 18th. Who wants it today? Nobody wants it today. Who wants it next week? Next week? Okay, 0, 0. Who wants it on 11th? 0. Who wants it on 18th? Okay, so it's going to be on 18th. Then our exam will be on April 18th, 14:30 to 16:30. Okay, so it's not next week but the other week. For some reason, student psychology, it is always better to delay it one more week. I mean, I bet if I do this 25th, everybody's going to vote for this one, but I am not saying no. Okay, so this is everybody. Okay, good. So whatever I can cover this week, next week, and the other week will be included in the exam. Good. So let's start this week's lecture. Last week we talked about edge detection, and when we say the edge detection, we talked about sudden changes in the brightness intensity, right? That's what the point of the edge detection. And it was, and some of you didn't like the idea much. I know, well, you didn't tell me that, but the way you looked at my slides, you were like, why are we doing this? What is it so useful? I mean, are we taking this course for this kind of stuff? Well, yeah, and yes and no. Well, without knowing the edges, it is not that easy to look at the other more complicated, more abstract features. And we defined the edges like this. We said that the edges are sudden changes in the intensity. For example, these are edges, right? These positions. Where is my? Yeah. Oh no, here. I need to draw it. Draw it. Yeah. These positions are my edges. Each one is an edge. And I know the orientation. These are the edges. Okay, so as you see, there are many edges in this image, but when you say find me a small guard house, what do you call this? Is this a guard house? I don't know what it is, but the guard stays there. Okay, find me a guardhouse in this picture. I mean, the edges will not help because there are so many things. I mean, edges will not be that helpful. In this lecture, we are going to detect other image features and we are going to call them corners. Okay, corners are much more distinctive. Okay, they can say much more about our objects other than the sudden changes in the image intensity, and the corners will not be enough actually, and we are going to put more data on the corners, and we are going to say other than they will behave like corners, but they will carry more information than the corners, and then we are going to use them to recognize our objects, and that will be our first object detection technique. So let's do that then. Let's start from the corners. Harris corner detection, and Harris corner detection will detect the corners, but your corners, the idea of your corner and the Harris corner are two different things, but they kind of overlap, but they are not exactly the same. SIFT is going to build on top of the idea of the corner Harris corner detection, and it will be something very useful, and it is very widely used. Okay, so you remember this one, Laplacian of Gaussian. We take the second derivative of the Gaussian, and it looks like an edge detector. Remember, this is used for detecting the zero crossings of the second derivative of a smoothed image, and it is done in the same shot. One filter pass, and nice thing is this is separable. What is separable? What's the separable filter, and why do we like them?
We can apply it on different axes.
Yeah, we can separate. Instead of applying two-dimensional filter, we apply one-dimensional filters perpendicular to each other, which is much cheaper than the two-dimensional stuff. That's why we like it. That's the definition of the separability. We like it, and if we do the Laplacian of Gaussian, Laplacian means the second derivative. Okay, Laplacian of Gaussian zero crossings are going to give us these nice edges, very nicely done. But the edge detection is not something that useful in terms of doing the object detection. Let's try to do something more. Let's try to detect the corners, where are the corners? For example, I have a corner here. Do you see it? Do you see it? You don't see it maybe. Corner here, corner there, right? And corner. Edges are different. Edges are like these. There are many edges. These are edges. I don't know if you are seeing it. Yeah, these are my edges. But corners are more interesting, and we are going to find corners. Okay, so we did the filtering, linear filtering from the filtering we have the edges. Now we are going to look at the furthers. Okay, and last time I think I talked about this stuff. Okay, why we are doing this. Once we detect this kind of, for example, these are the corners in this image, detected corners. You might say that, how come you didn't find this corner, and how come you didn't find that corner? You may ask that one. Also, you may say that, well, this is not a corner. Why do you mark it as a corner? For example, why is this a corner? I don't see anything different from the neighbors. Well, I don't know either. And you might say that, how come you didn't find any corners here or there or where else? I don't know. So I cannot, there are false positives and there are false negatives, right? I don't know why there is a corner. Well, algorithmically we would know, but I mean the idea of our corner is different than the idea of the corner of this hardness corner detector. For example, you would expect a corner here, right? Do you see it? No, you don't. You would expect a corner here, like that. But I couldn't find it. Anyway, so let's look at the definition of the corner. Corners are important because, as we said before, okay, there are two frames from the same video sequence. I am in a car and I am taking a video of the surrounding area. Okay. While I am moving, I took this video frame. Okay, these are my video frames, many of them. Okay, my car is moving and I am taking this video. So this video frame is here and this video frame is there. Right? Two of them. Okay, so if I can find the correspondence, if I can say that this point here, okay, corresponds to this point, okay, then I can use this idea of triangulation to find the depth of images. It is like this. Remember our simple camera. Let's say this is our one-dimensional camera. In the real world, if this is my object, and what I do is just do this, and this is my image point, okay? So this image point will not tell me much about where this object is in the real world, because it could be anywhere here or there on this line. But if I have a second view, and if I do this, okay, by intersecting these two lines, I know that object is from these 2 points. So it's called triangulation. So that's going to be very helpful in terms of finding the triangulation. So finding this kind of repeatable, distinctive point is very important for us. It is for image alignment, 3D reconstruction, this is called 3D reconstruction, motion tracking, object recognition, and etc. And in fact, I think I am going to give you one object recognition homework for the next homework, maybe. Yeah, that would be a good one. Okay, your second homework is object recognition homework. Since I am going to tell you about this object recognition, and if I am not finished, I will finish it next week. And by the way, I assigned the graduate student paper. I listed the requirements for the graduate student paper task. There are 2 phases. One is at the end of the next month and the end of May. Then you are going to present them after the finals. Now your second homework is coming. I didn't finish it yet, but okay, this is your homework number 2. Okay, do object detection using SIFT. And what should be the, like 18th is good? 18th? You like 18th? Maybe 26th, maybe 24th? Yeah, 24th is good. Okay. I will fill that in. If I forget, you remind me, okay? So your second homework is going to be object recognition. You are going to find these kind of distinctive points on objects, and when you see a new environment, new scene, you will try to find those objects, those distinctive points in the same object, and you will say that, okay, this is my object and this is my object, etc. Okay, so object recognition, you will know what it means. This is one example, image stitching. We talked about this last time. Let me skip these parts. No, this part is important. Okay, with the corner detection or these kind of higher level feature detection, higher than the edges, of course, there are 3 phases usually. Detection part, okay, find the distinctive points. What do I mean by distinctive? I found a point on this image, like this part, which looks very different from the other parts of the image. Okay, I am not saying it is unique. I am not saying that you cannot find any other points similar to this one other than that one, but it is distinctive enough. Why am I doing this? I am doing this because if I find the same distinctive point on the other image, I can match them together and find an homography between these two. Okay, it looks like this point is not visible in this image, but this distinctive point is available there, And as you know, it takes only 4 points to find homography between these two images. Once you know your homography, and you establish your homography, and you can stitch these images. Image stitching could have been your second homework, but I'm going to do the object recognition. Okay. The other thing is that after you find your distinctive points, okay, what kind of features do I have here? Okay, I have maybe X and Y positions of it, maybe the intensity of it, maybe the surrounding window, 3 by 3 window, right? So the total of X, Y, 3 by 3, 9, 11 numbers. Can I represent this point with 11 numbers? No. We don't like it because representing a point like that one, using a window around it with the XY position is not a good idea. We need much more expressive way of explaining the representing the point. That's called the description. Okay, so we will describe that point, for example, using 128 dimensional vectors. So we are going to say that for that point here, I am going to give you a 128 dimensional vector. This vector will represent this point, and if you think that you found the same point on the other image, you can compare these two vectors, and if these two vectors overlap, okay, then I can say that these 2 points are the same. So that's called the matching. So this distance function maybe is doing, this is 128 dimensional vector, and this is another 128 dimensional vector. I don't know, maybe just subtract it from the one from the other one. Maybe after subtraction take the square. Maybe look for the angle between these two vectors. I don't know what you're going to do, but if these 2 points are similar, then their vectors should be similar. Okay, if they are similar enough, then I will say that these match. So that's called matching. So we are going to matching this kind of we are going to we can't do much about it because there are very nice ways of finding the similarity between the vectors, but for the detection and the description, yes, we are going to work a lot. Okay, so let's look at this distinctiveness thing. The points that we are going to find should be distinctive. Okay, so we want to be able to reliably determine which point goes to which. Okay, I mean, if I find an edge here, can I find the same edge in the other image? Well, I mean, edges are very simple stuff. I mean, they have intensities, they contrast. Okay, so let's say one-dimensional image. There is an edge here, right? So if this is 100, the intensity level, and if this is 200, I know that there is a 100 intensity level drop at this edge, and there is an orientation, nothing else. So the distinctiveness of an edge is not that much. It's a nice feature, but it is not that distinctive. We need something more distinctive. When you say I found a point, okay, it's a distinct point. You can't find another point with the same features. It is not that distinct. So the first goal is distinctiveness. Okay, second point is repeatability. I mean, if I found a distinctive point around here, I should find the same distinctive point in the other image that contains the same point of the real world. Okay, so it should be repeatable. It should be distinctive. It should be repeatable, and it should be efficient. I mean, I shouldn't run my computer for 2 hours to find a point in my image that is distinctive and repeatable. Okay, so it should be compact and efficient so that I can run it on simple hardware in real time, maybe. Okay, so let's look at this slide. I think last time so your homework is basically this. This is what you're going to do. Let's say this is the object that I am trying to detect on images like that. This is my object, and this is the new image that I am trying to locate my object on, object detection. Well, the same thing. Okay, this is my truck, and I'm trying to find this truck on this here. Let's see. As you see, there are lots of clutter. We call this clutter. I don't know what the Turkish word exactly for clutter. Kalabalık. What is, ne Türkçesi ne clutter'ın ya? Kirli. Kalabalık, kirli. Siz cep telefonu ne için kullanıyorsunuz? Yazın nereye? Clutter.
Dağınık hocam.
Ne? Anlayamadım. Dağınıklık. Okay, so there is a lots of clutter from the other objects, like there is a cup, there is a book, there is other stuff. So it is not that easy to, I mean, you would say if I put these images on top of each other and subtract it, no, it won't work. Why? Because there is a rotation involved, and the point of view is different. I am looking at this truck from some other angle, right? It is different. So the idea is find these kind of distinctive points. For example, my detector says that this is a distinctive point around this region. Another distinctive point, another distinctive point, another one, another one. Okay, there are total of 5 distinctive points, and on this image I found these 3 distinctive points. And what did I say? I can get very good descriptors for these distinctive points. And if I compare the distinctive points of these 3 points with these 5, I see that there is a very good match between these 3. So that means that it is very possible that, it is very likely that there is an object like this on this image. There is an object like this on this image. Kind of very primitive object detection method. Okay? So after today, we will be able to do this kind of object detection stuff. As you see, these distinctive, repeatable, efficient detectors are robust against image rotation, okay? Lighting changes, this is darker image, right? Lighting changes, scale changes, this is a large image, smaller image. What else? Viewpoint changes, we already talked about, okay? Of course, if I have seen the other side of the truck, I don't have any luck yet because I didn't see the other side of the truck myself either. Okay, good. Any questions so far? So let's start talking about, okay, distinctiveness, repeatability, and compactness and efficiency. Okay, let's talk about some of these detectors. First, let's talk about this detection, the basic idea. Okay, so we do not know which other image locations the feature will end up being matched against. That's why, okay, when I say this, okay, when I say this, detect distinctive points from this image. When I'm working on this image, I didn't see this image yet. Okay, this is all I have. I've never seen anything like that yet. I am only seeing this one. So you are going to detect your distinctive points by looking at this image only. Okay, that's what we are saying. Okay, that's the basic idea. We do not know which other image locations the feature will end up being matched against. Okay, but we can compute how stable a location is in appearance. So we can say that I found a distinctive point because if I look around, everything changes, everything is different. Okay, so the strategy is I am going to compare it against all the other regions in the same neighborhood. If I say that anything around it doesn't look like it, so this is a very special point. Okay, this is a very special point, and that's where the idea of corners come in. Last time I think I kind of made an introduction on this one. Okay, so take this image. There is a corner like that. Okay, this is the image. There is a corner like this. This is a corner, right? And I have a window. This window, let's say, is a 5 by 5 window. It's a 5 by 5 window. Let me make this 5 by 5. Okay, it's a 5 by 5 window. If I move this window around a little bit, left, right, up, down, okay, all this window sees is just black image, right? Nothing changes. So I can say that maybe this point at the center is not a very distinctive point. Why? Because it doesn't make any change if I make this movement. Okay, so this flat region is not interesting to me. But even in fact, if I do the edge detection, this flat region doesn't produce any edges. Even for an edge detector, this is not interesting, which is right. How about this point? Okay. If I place my 5 by 5 window around this region, okay, if I move this window up and down like this, nothing changes, right? I am seeing exactly the same thing. Move this window 1 pixel up or move this window 1 pixel down. It is exactly the same thing, but if I move this window left and right, lots of things changes, right? My image changes. I am seeing different things. So kind of interesting, but only in one direction or one of the directions, nothing changes. So these kind of places are called edges. In edges, we say that no change along the edge direction, and the window changes its content in the other directions. So these are the edge points. Well, it is better than flat points, but it is not that distinctive either. Interesting points are these kind of places for me. Okay, again, 5 by 5 window. I place it around here. Doesn't matter where you move your window, left, right, up, down, diagonals. Your image, for example, let me move it like this. Let me move it. So I moved it to the northwest. I got this now 1 pixel only. So the content of the blue window and the content of the green window are very different, right? So it changed. Doesn't matter where you move your window, you will see a different image. So we like this one. That's what we call a corner. Okay, that's what we call a corner. You might say that. Let's say I have an image. This is my image. Inside my image, I have such a structure. Okay, this part is kind of dark. The other part is not that dark. Okay, like that. And if I place a window around this region, and if I move it left, right, up, down, it will be different, right? So it looks like a corner region. So you might say, well, this is not a very sharp corner. Well, that's our definition of a corner. When you move this window left, right, up, down, any place, if your window changes, content changes, we are going to call it a corner. Like this looks like the definition of our edges. How did we define the edges again? We said that if there is a sudden intensity change, we call it an edge. Okay, in any direction. But this one says that if there is a sudden window content change in any direction, that's what we call a corner. So the definition is much more strict than the edge itself. Okay, so that's called the corner detection. That's what we are going to do. Okay, basically, I mean, of course, when we are done with this corner detection, we are not expecting to use this feature to detect the objects yet, but that will be our first step. Any questions so far? So you might say that, let's do this then. Let's do this. Let me ignore this part. Forget about this part. Don't see this. How come this is so? Maybe I should do it. I need a black pen. Duplicate it and make it black and maybe a little bit thicker. Yeah, this is good. So let's ignore this part. Okay, this is what we are going to do. Let's say our original image is okay, I, X, Y, okay, for any part of the image. And I am moving my 5 by 5 window in the direction of UV. Okay, let's say if this is my image, on this image, if I have this window, let's say 5 by 5 window again, if I am moving my window in this direction UV, U and V, okay, I write this function. This function will take UV values, okay. It will say that I am going to subtract this IXY from I X plus U, Y plus V, and I'm going to do this for every value in this window. So this thing will iterate over 25 pixels, okay, because this is a 5 by 5 window. For every XY values in this window, I will do this subtraction and take the square of it. Okay, so question for you: if U and V are 0, what would you get from this summation? I am asking is what is E00?
Zero.
Exactly 0. Doesn't matter what kind of image you have, E00 has to be 0, right? Because U and V are 0, and that's it. How about E11? That means that I am moving my window to the down, because Y is 1, and to the right. Okay? Well, you are going to say, I don't know what the value will be, because this depends on the image. Right? This depends on the image. And how would you calculate this one? So what are you going to do to calculate these kind of E's? This is, okay. Again, let's ignore this one. Don't say it. This is my original image, okay, and my window is this. Let's say this is 11 by 11 window. If I move this window around, it will okay. If I move this window with this amount, E00 is going to give me 0. How about E10? I will shift this window to the right, just 1 pixel, and do all that calculation. Oh, sorry, it's not 0, I don't know. Do all that calculation, and it will give me a value A, and I will do 20, and it will give me a value B. Well, I mean, I'm going to do it for all the XY values inside this 11 by 11 window, and surprise, this is what I get. This is the E function. Remember that E function, this one, shown in its image. As you see, E00 is here, and it is all black. Why? Because this is 0. Do you see that 0 in there? No. Let me write it 0 like that. Okay, this is 0. Okay, so look at this image and tell me why this area is bright, and tell me why this area is, well, okay, let's start from that one. Tell me why this area is black, white, bright.
There is an edge or a corner there.
Say it again.
There is an edge or corner there.
Well, your original image is here. Do you see an edge or corner?
Intensity change.
I mean, you see everything that you need to know. Okay, I am not hiding anything. This image, this EUV image is driven from this image. Why? What is this? This one. This one says that if I move this red window up, up and a little bit to the left like that, Okay. If I subtract each corresponding xy values between these two, you are going to get a very large difference. Why? Because the center of this new red window and the center of this one are very different, and all the others are very different, right? That's what it says. But if I move this like that, okay, it's kind of similar, but that's what it says. That's the UV window. Let's look at some other examples. Let's look at this one. Yeah. Yeah. This point. This red. Let me mark it with blue. Okay. What kind of EUV window you would get for this region? Let's say this is again 11 by 11. At the center it will be 0 again. It will be something like, let me show you that. It will be something like this. See? Along the edge, everything will be close to 0, because if I move my window, if I move this window along this edge, okay, along this edge, this green line, nothing will change. Well, things will change, but it is not much. Okay? But if I move this perpendicular to this green like this red, okay, like this red, many things will change. The differences will be different. So that's why your UV will be like this. Along this edge, everything is dark, close to 0. But if I move in the other direction like this, things get bright because the differences will be high. So this is kind of, we found an edge. Let's look at some other places. For example here. Doesn't matter where you go in this case. Doesn't matter where you go. Okay? Things will be very similar. Right? Things will be very similar. So I am expecting a dark EUV image like that one, right? That's the other place. How about that should be okay here. How about this place? If my center of the image is here and this is my window, doesn't matter where you move, things will change drastically, and this is what you will end up with. Okay, only the center part is dark, so wherever you go it will be different. So out of these three, which one would you call a corner?
Middle.
Is middle one a corner? I think the middle one is an edge, right? It's an edge. Why? Because if I move in the direction of the blue line, it behaves like this. Right? Nothing changes. But if I move in any other directions, it will be differences. It is this one. This one looks like a corner. Why? Because only in the center it is 0. So wherever you move, it kind of concentrically, okay, the values gets larger and larger, kind of. Well, you might say that these are kind of dark, but it is higher than 0. This one is not. This one is everything is wherever you go, okay, it is all blackish kind of stuff. And if I draw this image like a three-dimensional map, did you understand how it is drawn? Did you see it? So this is our x dimension, y dimension, and instead of showing the brightness, I am showing the brightness like a height. So this is a three-dimensional surface. So edges are kind of valleys, right? There is a valley going through in this one. Corners are like dips, so wherever you go, it always goes in like that, right? It's like a dip, and the other ones are like the plateau. It is all the same levels most of the time, okay? So to find the corner, I am after this kind of a place, okay? So find an EU such that, that it behaves like this. Center is dark, of course. Everybody has anchor is 0. But when you move around, when you get away from the center, things start getting higher and higher. Okay, that's what we are going to find, and that's what we are going to call it as a corner. So I kind of give you the algorithm. Algorithm is calculate this window for a given point, and if it looks like this, we call it a corner. Otherwise, if it looks like this, it is an edge. If it looks like this, it's a corner. If it looks like this, it's a flat region. So I made an edge detector and a corner detector, but the problem is this is too expensive, okay? For every point, again, ignore this one. For every point, okay, I have to do, okay, in my image, I have my window width, I have my window height, okay, and for each part, for each point of the image, I have my window, okay, window dimensions, and I need to multiply all these numbers, and I need to take the square because these are rectangular square places. So for a 600 by 600 image, I need to do 5.2 billion multiplications, and that's not going to be very easy. Even if you have a fast machine, that's not going to be. So we need to find a way of saying that, okay, this is a corner EUV, this is a edge, and this is a flat, but without calculating these images explicitly. So we need to find a smart way of doing this. That's what the Harris does actually. Say that I'm going to give you, okay, I'm going to model this like a three-dimensional surface. So wherever you come, it always drops down to a lower place, okay? Once you detect it, I'm going to tell you that you found a corner, okay? So that's what we are going to do. But before we start doing that, I think I'm going to take some break. Any questions? Okay, let's take a break. After the break, we will continue. Yoklamayı daha vermedim. Evet.
Graduation students için TYT okuma ve şey var ya,
evet.
Ben şu anda TÜBİTAK'ta şu an çalıştığım bir proje var zaten. O projeyi zaten şu anda araştırmak istiyorum. Evet. Simülasyon üzerinde oluşturuyor. Çok şey yapamam, böyle şimdi yaptığım kanun dersler var. Tavsiyenin geliştiğini diyor. Tekerlik
Gelecek ders getireceğim. So, with the Harris corner detector, the basic idea is this: finding the corner windows where, yes.
Şimdi bağlantısı kopmuş olabilir. Bağlantı sonu sesi geliyordu da.
How about this one? No, this one. There is a problem with the, yeah, we don't have internet connectivity. Let's see if I can get it. This one is okay. No, we don't have the internet connection. Well, I am recording it locally anyway. I'm going to post it on the YouTube. So the corner detection thing is about finding 2D windows where there is some form of 2D texture, spots corner within the window, like this place. Okay, this is a flat region, this is an edge region, but this is a corner region. That's what we are going to do. Okay, so maybe I should get rid of these drawings where I don't remember when I did these. Clear them. Okay. So here in this case, I am going to, okay, do this summation over some region around this ij, okay, for all the uv values. Ij is there. Given this uv, I will move my window here, so I will take the difference between these two windows. That will be my uv value, okay, for the uv. For all possible uv values, let's say from -3 to +3 for all the uvs, I am going to calculate and I sum them up, okay, and that will give me my uv value. So I am trying to find image windows where uv values other than the 0, 0 is very, very different from 0. That's what I'm trying to find. So again, we can do it using the summation, a few simple loops, nested loops, but that will be too expensive. Instead, again, we are going to use some mathematics. Do you guys remember this? If I like to calculate a function at this position where I know that fa is and x is a very, very small value, right? So this is my function. I know what fa is. This is a, this is fa. Okay, and I like to calculate the function at this point, and this is, okay, just the difference is a plus x. Do you guys remember this? What is this? This is fa plus x is equal to what? Why do I talk in English?
What?
Do you think I like talking in English?
I forget.
Okay, so what do you say again?
I'm saying Fourier transform, but probably not.
No, it is not. Of course not. Do you see any sines and cosines?
No.
What is this? Nobody knows this?
It's like binomial, but I'm not sure.
It's no, yeah, well, yeah, it looks like it, yeah. Taylor series expansion. I think this is one of the first or second things that they teach you in calculus course, right? Taylor series expansion. You can approximate a function like this. You will say that I am going to where does it come from? It comes from this. You will say that if I know this function fa at this point, if I take the derivative of this one, okay, if I take the derivative of this function at this point fa, it will give you this line, right? And if I multiply it with this amount x, that will give you this much drop. Okay, this much drop. And if you add it, that's what you're going to get, fa plus x. But that's kind of an approximation. If I continue this, you will have to take the second derivative and the third derivative, and it goes until infinity. But usually we do this, and that will be it. That's what we are going to do. We say that if we are going to do this, evaluate this I plus u and j plus v, we say that, okay, it is enough for us to take the first two terms of the Taylor series expansion, okay, but our function is not a one-dimensional function, it's a two-dimensional function. So let's do this, ij plus the derivative of I in the x direction times u, derivative of I in the y dimension times v, that will be kind of equal. Okay, so it is exactly the same thing. Previously it used to be fa, but that's the single dimensional function. F prime a, the derivative of function with respect to x around this point a over 1 factorial is 1, and this is the difference between x and a. Okay, so that's what we do. So what am I going to do? I am going to put this approximation here. Okay, it will be this. Well, it turns out that this one and this one is equal, so I end up with this one. Derivative of the image in the horizontal axis times u plus derivative of I in the vertical axis times v, take the square of it. I can expand this expression, so if you expand it, you get this one. So the square of the first part and the square of the second part, and 2 times ix, iy, iy, uv. Okay, so this is not a very complicated expression actually. So, okay, tell me what we know about this expression. Which ones do we know and which ones we don't? I can definitely calculate the derivative of an image in the x direction and y dimension, right? I know those. And I can take the squares of it, right? I can take the squares of it. For each uv value, I can put these in, and that's what I am going to get. So it will be very, very easy to calculate. It will be very, very easy to calculate this expression actually using these derivatives. But we are not going to do it that way. We are going to do it this way. We say that this expression and this expression is the same thing. Just take a moment to see what's going on here. So it's just a vector, a matrix, a horizontal vector. So if you multiply this vector, okay, with this, do you want to do it? Okay, let's write it. U times ix square, then v times plus v times ix iy, that will be my first element, and the second one is u times ix iy plus v times ix v times iy square. Okay, that will be the first part, and the second part will be u and v. And if I multiply this one with this one and this one with this one, you are going to end up with this 3-term expression. So you are going to ask why are we doing this? I mean, if these two things are equal, why are we doing this? We are doing this because in this matrix I don't have any UVs. So this matrix is independent of UVs. I don't see any UV values. Okay, those vectors. It is all about the image. Okay, it is all about the image. That means that given an image window, I am trying to see if there is a corner or not in this part of the image. Okay, I will calculate these values, and after that, by multiplying those values with the UVs, I can get whatever I want, or I can be more smart and I can do some other stuff, but I will show you. So the thing is that I can get, how do I calculate the x derivative? So x derivative ix is just simply subtract this value from this value for the iy, subtract this value from this value, okay? That will be the iy. Just two things for a single pixel. I calculated this matrix. Then I can multiply it with this UV values, whatever I want. It's the same UV, 5500, whatever, okay? And you are going to get this difference, okay? So instead of doing that many loops, I can use this approximation. You might say that, well, this is only an approximation. Well, approximations work if the final results turn out to be okay, and in this case we did the experiments, so the final results turn out to be okay. Okay? So, but again, I am not going to calculate those, okay, remember that E windows. I am going to do something else. Can I go directly from this matrix to the corners stuff? Okay? So this is what I get. By the way, this is only a single pixel. Remember, this is only a single pixel. If I do this difference on a window, then this is what I do on this window. Okay? Ix square, all the additions of it, Iy square, and this and that. Okay, so this is my matrix that I am dealing with. Again, this is a 2 by 2 matrix calculated over, for example, 5 by 5 window, or 7 by 7, or 11 by 11. Okay? So, this matrix C characterizes how intensity changes in a certain direction. And that direction is this direction. Maybe we can analyze this matrix to see, what kind of directions are important for this matrix. Okay? Let's look at this one. Let's say this is I am going to use my blue color because let's say I have 4 values, A, B, C, D. Let's say this is U and V. Okay, 2-dimensional vector, a 2 by 2 matrix. If I multiply this, it's going to give me, okay, it's going to give me another one. Let's say X and Y. So we are kind of doing a transformation. Remember the transformations? A 2 by 2 transformation, it does the rotation, for example. Okay? It does the rotation, it does the scaling, we can do whatever we want. Okay? And we are going to say that if you are a matrix, like 2 by 2 matrix like this, are there any special UV values that you like, or are there any UV values that are special for you? Do you know this problem from anywhere? Can you ask these kind of questions to the matrix here, right? Are there any UV values, like the XY values, that are special to you? And sometimes these square matrices says, yeah, I like these are kind of special for me. Do you know this problem? Do you remember this problem for the matrices? From your linear algebra course? Maybe you will remember this. If let's say this is a matrix, 2 by 2 matrix, and this is a vector, just 2-dimensional vector. If I do this multiplication, if I get something like this, lambda is just a scalar. Okay, what does that mean? X is such a dimension, such a vector, okay, when it is multiplied by this matrix A, you don't change X's direction. X stays the same, only you make it longer or shorter. If this is my X vector, when I transform this vector with A, all you can do is you either make it short, long or short. Okay? So that means that for this matrix, X is a special one. Okay? What is this problem? You know this problem. That's the most basic thing that you learned in the calculus course is the Taylor series expansion. You didn't know that. And I am asking you the second most basic thing that you learned from your linear algebra course. What is this problem? Come on, you are joking, right? She's joking, yeah. What is this problem? You don't remember? It starts with an E.
Identity vector.
Is identity starts with an E? Yeah, it depends on how you write it, yeah.
Eigenvalue?
Eigenvalue problem, exactly. This is an eigenvalue. Who said that? Okay, eigenvalue. Why did you wait?
I just remembered.
You just remembered? Okay. It's the eigenvalue problem. Eigenvalue is looking for such a, you say that if you have a square matrix like this, for this matrix, if you can find such a vector, that's a special vector for this matrix. Okay? We have a 2 by 2. We have a 2 by 2 matrix like this. If you can find special vectors like these that makes it this true, okay, then those are your eigenvectors. And let's look at this problem. We have 2 by 2 matrix, and if I can find those kind of special directions, those are special to me, and those will give me the directions of our corners. Actually, it will tell you that, okay, if this is a full rank matrix, okay, its determinant is just 2, full rank matrix, I can inverse it. You take the inverse of it, okay. You will find 2 eigenvectors, okay. One of them will be the one direction of the corner, the other one will be the other direction, because in the corners, okay, this is a corner, right? I have 2 directions. This is another corner. I have 2 directions. This is another corner, pointy corner. I have 2 directions again. Okay, so take the eigenvectors of this 2 by 2 matrix if you can find them. If you can find them, it's a corner. Okay, and the directions that you find for that eigenvalue problem, or the vector or the eigenvectors, will be your directions of the corner. That's what it says. Okay, so that's what we are going to do. We are going to find the eigenvectors and eigenvalues of this 2 by 2 matrix. And if we are lucky, there will be 2 eigenvalues. If we have 2 eigenvalues different from 0, that's the eigenvalue analysis, right? If we have 2 eigenvalues, okay, that means that I will have a corner in this region. If we have only 1 different from 0, that will be an edge. If there are no eigenvalues, if it is all 0, then it's a flat region. It's a flat region. Let's look at this actually. Without making any eigenvalue analysis, if I have a window like this, and I am going to draw this 5 by 5 window, 5 by 5, right? So this is all black, let's say, and rest of them is white. White will be painted like this. Okay. If I take the derivatives with respect to x, and if I take the derivatives with respect to y, okay, for this point, for example, the derivative with respect to y will be what? This one. The derivative with respect to y will be 0, exactly. But the derivative with respect to x will be non-zero, right? Because there is a change. How about this one? Derivative with respect to x will be 0, but derivative with respect to y will not be 0. So for some pixels, like this one, this one, this one, this one, okay, their derivatives, okay, either x or y dimensions are non-zero, okay. But for the others, like these regions, all the derivatives are all 0. So if you visualize it in your eye, so you are going to see that no pixel will have a derivative of x and y, non-zero x and y. So this will be 0, right? This will be 0. So this will be non-zero and z, and this will be non-zero. So you will end up with this kind of a matrix: 0, 0, a number there, a number there. So obviously there is a corner there, right? I know this. Obviously there is a corner there. I mean, it is not that difficult to see that there is a corner, and this matrix will produce it. The problem is this: what happens if my window is like this? Okay. So, well, I'm not doing it right. Sorry. So it is all black here, and the rest of them is all white. So it looks like for some of the pixels, both x and y derivatives are non-zero, right? Some of them. And I know that, well, in that case, this will be non-zero, this will be non-zero, this will be non-zero, and this will be non-zero, right? So you might say that, well, I know that there is a corner, but how about this one? How about this one? Do you see any corners in this window? No. But for some pixels here, both x and y derivatives will be different from 0. So in the summations, all of them will be different from 0. So by just directly looking at this matrix, you will not see that if there is a corner or not. Okay. So we are not lucky that in this case we were lucky because our corner is axis aligned. In this case, we are not that lucky. In this case, we are not that lucky. Okay, we are not that lucky. Let's look at this one actually. Let me draw this one. In this case, my image left side is dark and right side is all black, like that. Okay. Around here, all the pixels with a derivative in the x direction but no in y direction. So it will be, this element will be non-zero, 0, 0, 0, and you will see that there is an edge, right? But this is on axis aligned edge. This is not an axis aligned edge. So how am I going to say that there is no corner in there? So this is what you, okay, you are going to get this matrix first. Okay, you are going to ask how many special directions are there for you, and eigenvalue analysis will tell me if there are 0 or 1 or 2. For this one, there will be 2 special directions. For this one, there will be 2 special directions. One of them is this, the other one is this. For this one, there will be only 1, and for this one, there will be only 1. Okay, that's what the eigenvalue analysis will tell you. So with the linear algebra analysis, okay, this is the, remember, this is the eigenvalue problem. AV equals to lambda V. Okay, V is eigenvector, lambda is eigenvalue. Another way of writing it is this way. The the linear algebra people write it that way. Okay. So one of the cool things is that we can use matrices to do transformations. I know that. Okay. So this is just a transformation of V with a matrix A. I'm simply asking, what kind of V can I give you so that you cannot change the direction of V? A says that I can do it in two ways, okay? Either this corner or that way, or it says that I can do it only one way. That means that I have a edge in that case, okay? So in that case, the eigenvector is a direction that doesn't change the direction. Okay, so eigen means, what do we call it in Turkish? Eigenvalue analysis, eigenvector analysis, özvektör analizi. Why are you looking at me like that? You didn't see this eigenvalue problems? Didn't you spend like a month for the linear algebra course to calculate these? What? Özdeğer, özvektör. Yes. So it is used for, when you do the eigenvalue analysis of a matrix, it tells you what kind of information it contains, okay? And usually, if you have n by n matrix, square matrix, if it's a full matrix, okay, it will contain n special directions and n values on those directions. So basically, if you like to know what a matrix is composed of, eigenvectors are very important. That's what we are doing here. So there are many things, like if C is symmetric, in our case, is our C symmetric? Remember that matrix. Our matrix is IX square, IY square, IX, IY, IX, IY. Don't forget this. Is it symmetric?
Yes.
The answer is, of course, yes, it is symmetric. If C is symmetric and square, okay, are also diagonalizable if some matrix P exists, such as this. So P minus 1 times A times P, where A has only diagonal entries. So A will contain our eigenvalues. P will correspond to our rotation matrices. Okay. So in our case, for this one, okay, when I look at the C matrix of this case, it will be C equal to, I have enough, okay, R minus 1 times the center one. What did we call that one? It doesn't matter. Well, maybe I should use the same notation. We said, okay, A and R. So I can decompose C into these three matrices. A will contain my eigenvalues, and R is my rotation. So R will tell me about this angle. Okay, how I am off from the x and y. Okay, R is going to tell me about this and this angle, actually. How I am off from the x and y axes. Okay, so that's the eigenvalue solution to our original problem. If we go back to the original problem, in the original problem we are trying to calculate this window so that if it is similar to this, I am going to tell it there is a corner. Okay, I told you a method first, but you didn't like it because you told me that this is too expensive. So instead I am saying that let's calculate all those derivatives and put them in a matrix and do the eigenvalue analysis. And the eigenvalue analysis is going to produce me this. Okay. C is going to something that I'm going to calculate from the derivatives in the x and y directions. UV will be our special directions, okay? And C can be decomposed into R minus 1 and this lambda 1, lambda 2 and R. And actually this is a formula for an ellipse. Ellipse can be represented this way. This lambda 1 and lambda 2 will be proportional, negatively will be inversely proportional to the square root of the width and the height of the ellipse, and the direction of the ellipse, that is this, okay? This angle, or sorry, maybe this angle, alpha, okay, will be given by this R, okay? So that will give us the angle of our rotation, our corner, and these lambda values will give us the width and the height of this ellipse, if you like to see it as an ellipse. But it is inverse, right? It is lambda to the power minus 1 over 2. That means that if these values are large, this ellipse will have a smaller diameter. But if the values are large, that means that we have a corner or edge there in that direction. Okay? So these are the things. It can be shown that since C is symmetric, I can do this and get these values, and these values will give you both the direction of the corner, also the strength of the corner in two directions. If I have an image like this, okay, this is the image. Very simple image. Dark, bright, dark, bright. And if I run my window operator, let me do it, okay, here, here, here, here, here, everywhere, okay, and for each window calculate this ellipse and show it like that, okay. So remember the lambda values, they are inversely proportional to the width and height of the ellipse, okay. So ellipses are very, very small around here because there is a corner. Ellipses are very large here because there is no corner, okay. Ellipses are kind of large, but their width, horizontal width is high, okay. Their vertical widths are very, very small. So that's why we say that around here there are edges. Around here there are edges, but their directions are like those. But around here there is a corner. So this operator both detects edges and corners. It tells us the directions of the edges of and the corners too. Edges and the corners too. So the edges are horizontal here, edges are vertical there. Okay, that's the visualization. Oh, okay. Let me give you the summary of this thing. Okay, corner detection summary. So what we do is you take some window, 11 by 11 window, and you calculate this C matrix, which is, okay, summation of all the summation of IY and summation of IXIY, IXIY, all those summations. Okay, this is a 2 by 2 matrix, and do the eigenvalue analysis. That's going to give you two lambda values, lambda 1 and lambda 2. If you have two lambdas, that means that there is a corner in that window. If there is a single lambda, then that means that you have an edge. And if you have no lambda, that means that's a flat region. Okay? So you run this test for all possible positions on your image, and then that way you are going to find your corners. That's the corner detection summary. Okay, and this is a rule set that say that get your lambdas, lambda 1 and lambda 2. Okay, if both of them are large, then you have a corner. If both of them are small, near zero, you have a flat region. If one of them is large, you have a either vertical edge or horizontal edge. Somebody came up with this idea. Let's calculate a value like C, multiply those two with lambdas, and minus alpha times lambda 1 plus lambda 2 and square. That's going to give you a C value. If C value is large, then you have a corner. Okay. If C value is very, very small, then it's a flat region. If C value is less than 0, okay, then it's going to give you an edge. If lambda 1 is greater, it's the vertical edge. If lambda 2 is greater, then there is a horizontal edge. So we are looking for the sign of the C. Okay, if it is away from 0, then it's either a corner, or okay, if it is greater than 0, it's a corner. Less than 0, then it's an edge. Okay, this is called Harris corner detector. Harris corner detector. And this matrix, remember that matrix that I showed you before, is the Harris corner detector operator. And it has some other uses where we are going to see in a few minutes. But before that, I will take a break, 50 minutes. Any questions so far? Any questions? So nobody thought that eigenvalues or Taylor series expansion are useful things. You completely wipe them out from your memory. Is that? No, those are important stuff. And we are going to use them a lot, okay? Whatever you learned in your calculus classes or linear algebra classes, they are the summary of the summary of the summary of important stuff, okay? That's why they are very, very important, okay? We don't teach you important stuff. We teach you summary and summary and summary of the important stuff. So whatever they are teaching you, just learn them. Okay, 15 minutes. Let's be here around 16:40. And I am not going to forget about the attendance this time. Okay, so this will be our algorithm. Our algorithm will be Harris corner detector. We like to determine if each point is a corner or not. This is what we are going to. Let's say this is our input image, okay, and we are going to find the corners. Tell me where the corners are, okay. I am going to show you some corner. For example, this will be a corner. This will be corner and corner and corner and corner, corner, okay. And then these are the corners. I am expecting that these places will be corners. What else? Of course, corners here, the 4 of them. I don't expect any corners around this ellipse, but I am not sure. Maybe if the curvature is too big, maybe there is a corner there. And here I am expecting corners like those. Anyway, okay, so that will be our image. And the first thing we are going to do is take the image derivative in x and y directions. Ix and Iy is like that. Okay. Well, I mean, this means this is 128, right? Gray. It means like there is no change. It corresponds to 0. There are minus derivatives and plus derivatives to map into 0 to 255. This is what happens. So this is, as you see, there is a 255 here, and there is, okay, minus 255 there. And if I map it into 0 to 255, then this is what I'm going to get, right? So for the, see, this is funny, right? For the y derivative, there is no response in the horizontal axis, but yeah, you see it there, right? Do we have something? Yeah, we lost this one. See, we lost this one. Okay, go away. We lost this one in the Ix dimension. Good. How about this one? These are the squares of each pixel. Okay. Why do we need this? We need this because remember our Hessian matrix. In the matrix, I have both this one, that one, and that one. Okay. So I think it is this one. Well, see this one. This one loses this horizontal line and the vertical line too. You don't see them, right? This one loses the vertical line. This one loses the horizontal line. This one loses the horizontal and vertical line because I am multiplying them, right? Okay. And then I do all these calculations. I do the Gaussian filtering. Okay, that's what we do. Compute the image derivatives. Okay, optionally below first. Compute the m components as squares of derivatives, and the Gaussian filter of all the ix square, iy square, and ix times iy, and then calculate this. Okay, determinant of m and minus alpha times trace of m. Well, determinant of m is just lambda 1 times lambda 2, and trace of m is the addition of lambda 1 and lambda 2 with this lambda. And choose a threshold on C and mark all those positions as the corners. So this is what we get. Okay. This is what we get. Remember C, if C is less than 0, okay, if it is less than 0, it means it's an edge. Okay, if it is greater than 0, sufficiently greater than 0, it's a corner. Okay, let's look at this one. Around here, these are all zeros because I represent them with 128. And the corners are here, okay, you see the corners? Corner, corner, corner, because at these positions the corners. So let's look at this part. It looks like This one is reporting many corners. I mean, this is a maybe 1, 2, 3, 4, 1, 2, 3, 4. Maybe this is a 5 by 5 region, and inside this 5 by 5 region, everybody is a corner. They are all above the threshold level of, I don't know, C. Okay, so we need to do something like that. So what is your solution? In this region, 5 by 5 region, everybody is a corner. But I need just one corner in there. What would you do to eliminate this? I need an algorithm name. You will say that, well, we have seen such a problem before.
There was a Kenny H algorithm has a something like that.
Yeah, what do we call that? Non-maximal suppression, right? Non-maximal suppression. You don't see it? Okay, I read. Okay, non-maximal. So what do? You say that if my neighbor has a higher response, then I am not the corner, then he is the corner, right? And we are doing this, and everybody checks with their neighbors. And if one of the neighbors has the highest one, then we are going to choose him as the king. Okay, so that's what we do. That's the corner detection basically, and the corner detection will give you the corner points, and corner points are much more distinctive than the edge points. By the way, all the black stuff are the edges. These are all the edges. These are edges, and we know the directions. Okay, so this Harris operator, it detects both corners and the edges, but we don't like its edge detection performance. Kenny does better. And we like its corner detection capability than the edge detection capability. Here is one example, real life example. Okay, same object taken under two different conditions. There is a lighting difference between these two. Camera is rotated, right? There is maybe a little bit scaling difference, and I think they move the head a little bit. No. Camera is rotated, right? Camera is rotated. And I think the head is moved a little bit too. I'm not sure. Okay? So we are going to see if this object is the same as this object, or can I match it? Okay, for example, if I find a corner here, can you see when I say here? If I say, if there is a corner here, can I find the same corner like that? Okay. And if I find a corner around here, can I find the same corner around here? Okay. Like that. Okay. So that's what I'm going to do. Let's do the corner detection. These are the C values that are higher than some threshold. Remember, C is this. C is lambda 1 times lambda 2 minus alpha times, okay? If C is greater than 0, sufficiently larger than 0, then there is a corner, right? So these are some large C values. As you see, even for this reflection of the light source, we get lots of values, okay? And these are the results of that detection. Well, I didn't get any corner points out of this, you might say. Well, let's run this non-maximal suppression maybe. Okay. But this is the colorized version of the same thing. So blue means that C is less than 0. Red means that it is way above 0, and etc. Okay. So if you choose the maximum of them using the non-maximal suppression, you see these dots represent the non-maximal points. That is these dots represent after the non-maximal suppression maximal points. Okay. So these are the points, and see, I have 1, 2, 3, 4 points around the back of this. Is this a giraffe? What is this? Is this a cow? What is this?
Cow.
So it's a cow. And do we have, okay, 1, 2, 3, 4, 5, I guess 6. This one detected 4, this one detected 6. How many of them match? I think this one matches, right? This one matches, this one and this one matches. Well, 4 out of 6 is not bad, okay? So remember, if I try to do the same thing with the edges, I mean, there are millions of edges for this image. There are millions of edges, like edges here, right? Edges around these spots, edges around like that. There are many edges, but with the corners, the number of corners is much smaller than the number of edges, and they are distinctive. Okay, there is a hope of finding the same edge in the other image. Okay, look at these points. Okay, see, I found this one, and I found that one, and look at these points. There is a corner and there is a corner. There is a corner and there is a corner. See, I can match them easily. How do I match them actually? Well, I match them by looking at the, okay, this one says there is a corner and this one says there is a corner, and this one will tell me that there is a corner and the orientation of the corner is like that, and this one will say that there is a corner and the orientation is like that, and maybe I can compare the image regions around them to see if there is a match or not. Okay, so that's the end of the Harris corner detector. Any questions? Yeah.
Like three previous of 3 pages. Can you bring back the gap?
Which one? This one? This one?
Yeah, this one.
This one?
Yeah. I didn't get the whole thing of the m in the step 2. Compute m components as square root derivatives. How do we get the m? Like you showed us a matrix. There is a matrix like ix squared and ixy in the position of 1, 0 as a matrix.
Well, you know, for each pixel you have the ix, iy, and ixy, right?
Yeah.
And ix squared, iy for each pixel. But we are interested in computing these values in the square windows, like the sum of all of them. Okay? Because our C matrix is like sum of ix squares, right? And sum of iy squares. Okay? So that's how we calculate them.
The sum of all pixels, or
No, window. As I said, window for this one. To see if there is a corner or not around this point, I get a 7 by 7 window, and that means that I have 49 pixels in it. I add the ix squares of each pixel inside that window for this one, and for this one, for the y square, iy square additions, and this is the multiplication, that will give me the C matrix. Okay, and maybe I can calculate the Gaussian before doing those, depending on your preferences. Then do this. Determinant of m, or trace of m, is the, you know what I mean, those are the lambdas. Okay? So, if there are no questions, then I will continue. Well, Harris corner detection is much more distinctive. It is much more distinctive than the edge detection, but it is not as distinctive as we like, or it is not as repeatable as we like, because there is a matching problem. I mean, I know that I detected these 4 points and I detected these 8 points, but how how do I know that? How do I know that this point here corresponds to this point there, right? How do I know that? It doesn't tell me anything about how to match points between detected corners. There are many possibilities, and it doesn't give us that. So for that, we have this technique SIFT, scale invariant feature transform detector and descriptor SIFT. Okay, so it was at the beginning of the 2000s. Okay, this guy, Date Law, he invented this. Actually, they patented it. That's why nobody uses this. Nobody uses this as in a commercial product. And even in the papers, OpenCV, for example, says that I am not implementing SIFT because it is patented. OpenCV is a open source free library, so they don't include SIFT in their code, but you can later add it. But we have other detectors like SIFT. They do as good as SIFT, and they don't have this patent issue. Let's look at what SIFT does. SIFT says this, okay? When you translate this image from this point to that point, okay, our derivatives and our window functions are shift invariant. Okay, what does that mean? Our derivatives change, right? I mean, the derivative of this image and derivative of this image is different. I know that, right? So that's kind of expected. Okay, so our location will change with respect to image. That's kind of expected. Okay, how about this rotation? Of course, everything will change, but when you rotate an image like that, corner positions will change. But I can still, if I am saying it, if this is a corner, and I will say if this is a corner, then I will say this is a corner too. And remember our lambda values, lambda 1 and lambda 2. Those are the diameters of the ellipse in x and y dimension. Those diameters will not change from this image to that image, but the rotation of the angle of the ellipse will change. Okay, so the corner location is covariant with respect to rotation. Okay, so the corner location will change. Cornerness will not change. I can detect the corners, but corner location will change. Also, the corner angle will change. How about the scaling? That's the bad part, maybe. I mean, by rotating the image, I can still detect the corners. Their features will be changing. But maybe I can do some workaround about it. But how about the scale? For this one, there is definitely a corner within this window. But if I make this curve larger, this window, or this window will not detect the corner. They all say that there is an edge, not the corner. So scaling is a problem. Corner location is not covariant. Scaling is going to be a problem. So what does that mean? It means this: these two images, the cow, the size of the cow is approximately the same between the images. But if I make one of the cows smaller or larger by moving my cameras away from the cow or near the cow, then my corner detector will have problems, because corner detection, as you see, it runs on a 7x7 window, and you may not see the same thing. So that's a problem. Scaling. Okay. So the motivation of SIFT is this. Okay. Harris operator is not invariant to scale, and correlation is not invariant to rotation. Okay. So I am going to do this. I am going to develop an interest operator. Okay. A distinctive feature detector operator that is invariant to scale and rotation. Okay, so whenever you scale your image, make it smaller, larger, or rotate it, I am going to find the same point. Okay, and also For each point, I am going to give you a descriptor. That means that if I detected a SIFT point, sometimes I call the corner point, a SIFT corner point, I am going to give you produce a descriptor, like as I said before, 128 dimensional descriptor that will describe that point. You may use this descriptor. To match between the images. Let's say I have two images. Okay, image of the same object. I produced 100 SIFT points on this one and 80 SIFT points on this one. Okay, each one has 128 dimensional vector, and this one it has a 128 dimensional vector for each point. Okay, so I can compare these vectors with all the combinations, and I can say that this point corresponds to this one, and these ones, they don't correspond to each other. So I can say here, there, and some of them, they don't correspond to anybody. Okay, so that's a good thing. So that descriptor is a very nice feature of the SIFT technique, and in fact, more than the corner detector or the SIFT detector, the descriptor part of this method is used more. Okay, good. So previously, remember the picture that I showed you? That picture is directly from the SIFT paper. Okay, it says that my method, his method actually, he says that is going to detect these points are distinctive points, and each of those distinctive points can be represented using 128 dimensional vectors, and you can match them using the simple matching methods. And let's see how this thing works. Okay, so it says that I will be distinctive. Individual features can be matched to a large database of objects. Quantity is important. For a given image, I will produce you lots of points. So if I produce a 0 point or 1 point or 2 point per image, that wouldn't be very useful. I will produce lots of points. It will be efficient. You can run it in real time. Okay. It will be local. It will be local features. So that means that I am going to look at only small part of the image, 10 by 10 image or 15 by 15 image, not the whole image. Why is this important? It is important because sometimes some parts of the image is not visible, so I don't have to see the whole object to see it. Okay, and it is extendable, can easily extend it to wide range of differing feature types, with each adding robustness, it says. Okay, so these are the basic steps of the SIFT detector. Scale space, extrema detection, key point localization, orientation, and key point description. Let me talk about this orientation first. Okay, see this one. This one is rotated to the to this version. This one is rotated to this, and this one is rotated. See, it is kind of rotating. I guess this part is this part, right? So it is rotated clockwise, maybe around 80 degrees. How about this one? This one is kind of, yeah, I guess this part is this part. That's what I am guessing. For this one, this part is, I guess, this part. So this technique is doing the orientation correction too. And if I do the same thing for this one, see, this one, this part, well, okay, yeah, this part will correspond to this part. It is doing this rotation automatically. That's what I'm saying. So that's the orientation assignment. But at the last step, I produced that 128 dimensional vector for each point, key point description. And before that, I need to detect my key points. Where are my key points, the localization? But before that, I need to do something about the scale thing, okay? Remember scale problem? What happens if my objects are small in one image and large in the other one? And the solution for this one is actually simple. Don't look at the image in one scale. Look at your image in many, many different scales. Given your image, make it smaller, smaller, smaller, and smaller. And don't pick any scale. Consider all the scales at the same time. Okay? That's the idea of scale space detection. Okay, so let's look at this scale space extrema detection. Our goal is identify locations and scales that can be repeatedly assigned under different views. What am I going to do this? I am going to switch to scale space. This is my scale space. My images are two-dimensional, right? I, X, Y. This is how I represent my images. This is how I represent my images. I, X, Y, like two-dimensional image. This guy says that let's represent our images in 3 dimensions. And my third dimension will be sigma. This is X and Y. My third dimension will be sigma. And sigma is the parameter of a Gauss function. So when I increase the sigma, I am smoothing my image out. Okay? So I have this original XY image. I apply the Gaussian. Okay? And I place that image on top of this one. Okay? And I applied another Gaussian. I place it here. So my image became 3-dimensional. By 3-dimensional, I don't mean our XYZ dimension. I mean XY lambda dimension. Okay? So that way, I am kind of representing my detailed view of the world and my cursor view of the world. So I am taking away the details. Okay? And while I am doing this, maybe I can make my images smaller too. Okay? So bottom level is the original. Smooth your image and subsample it to get a smaller image, and smaller image. So these are called image pyramids. Using the image pyramids, okay, you have different representation, different scale representation of your image. If I can detect my corner points in this space, in this 3-dimensional space, then I will be insensitive to changes in the scale. Okay? That's the idea. So work on this image, not on the original image only. Harris corner detector only works on this image. Okay? But what happens if my next image is around here, right? That will be a problem. Okay, so this is what I will do. Bottom level is the original. We take these 4 pixels, take their mean and put it in there, and do the same thing with these 4 pixels and put it in there. So effectively, the number of pixels is 1/4 of the original one. Do the same thing. Of course, don't do it too much. You are going to lose all your pixels. That's called the image pyramid. And before we do this, taking the mean of 4 pixels, of course, I apply Gaussian, and this is what we do actually. So this is maybe the original image. Apply Gaussian and subsample it. Apply Gaussian, subsample it. As you see, this image loses all the information about this background. Even I can barely see the man's eyes. Okay. That's building the premise. So I am considering all possible scales of the same object. SIFT will work on this pyramid. But going from one level to other level, I mean just considering this raw pyramid, is not something that is useful. We need to do something else, and that something else will be very similar to our, remember our LOG operator, Laplacian of the Gaussian? Okay, remember this Mexican hat? What was this? This was the second derivative of the Gaussian, right? Gaussian is this. This is our Gaussian. And this is our first derivative of the Gaussian, like that. And then our second derivative will be that one. Okay? So that's the second derivative of the Gaussian, and we represent it this way. Okay? How much Gaussian you are going to apply will be determined by this parameter. Using this method, actually, they can do the blob detection. See, if I have a picture like that, using the scale-space approach, and by changing the values of that sigma, I can say that these are my blobs, blob detection. Blobs are kind of parts of the same object that are related to each other. These are my blobs, okay? And this is my scale dimension, okay? So when I go up in the scale, I am only paying attention to very large objects like these. These are large objects. But at the lower scales, maybe I am paying attention to small stuff like this. Okay? All of them are important, and all of them should be considered. Okay? Good blob detector. Some people say that instead of running Laplacian of Gaussian, I can get the same effect by difference of Gaussians. Okay? Run the Gaussian on my image with this parameter sigma. Run another Gaussian on the same image with this time k sigma, a little bit different sigma, and do the subtraction, and you are going to get almost the same thing as the Laplacian of the Gaussian. For example, it will be like that. Okay? So the Laplacian is the blue one. Okay, difference of Gaussian. Okay, difference of Gaussian will be the red one. So if it is cheaper to run difference of Gaussian, then I'm going to do that. SIFT does that. Okay, it does the difference of Gaussian. That's the main algorithm. Okay, it takes the image, it runs the Gaussian filter on the image at different levels. So this is the original image, blurred image, a little bit more blurred, a little bit more blurred, and this is the blurriest image that I have. If I take the difference between two, it's kind of running Laplacian of Gaussian, but it is of course the difference of the Gaussians, and I will get these results. So these are the kind of age detection results, if you like to call it that way. Okay, so this one is looking for the difference between these two images in the XY lambda space. And I do exactly the same thing in my second level in my image. Remember my image pyramid? Make the image smaller. I do the same thing in my second level and third level and fourth level and fifth level. How many levels you would like to do? Depends on your parameters. Okay? So let's remember what we did. We get the original image. We made it smaller. On the original image, I formed this Gaussian, this three-dimensional scale space, and I took the difference between each level, and I produced this difference of Gaussian images like that. Okay? So difference of Gaussians are kind of taking the second derivative of the image, kind of an edge detector. Okay? But these edge detectors, they run at very, very different scales because my Gaussian is changing, and I'm doing this with different resolutions of the image. And after that, I am going to ignore this part, and I'm going to work on this part of the data structure, and this is what I do. I take this one, okay? For example, I take this pixel here. I compare it with all the other pixels around it, 8 of them. Also, I compare it with the 9 pixel in this level, and I compared 9 pixel above level. So how many pixels are there? 9 plus 9, 18, plus 8, 20, 28. I compared with 28 pixels around it. If I am larger than all of them, that means that I am a special pixel. Because I am, as an edge point, I am larger than my neighbors in my scale. Also, I am larger than all the pixels in my layer, in my previous layer and upper layer. Okay, so that means that I am a special pixel. So I took that point as a corner point, SIFT point. That's the critical step of the SIFT detector. Okay, so that's the idea. This is what I do. Compare this with this 8 of these pixels. Also compare it with all the 9 pixels in the previous layer and the upper layer. And for each max or min found, by the way, oh yeah, well, I made a mistake there. I said if I am larger from all of them, then I am special. Also, if I am smaller from all of them, if I am smaller than all of them, I am a special point too. So for each max or min found, output is the location and the scale. So scale is this. Remember, this is sigma 0, sigma 1, and sigma 2, and sigma 3. The scale is important. Also, the location is important too. Detect maxima and minima of the difference of Gaussian scale space. And this is how it is done. So we basically found the position where it says that it's a special one because it's a result of the edge detection, and it says that I am larger than all the points around me, both in the scale and the other scales. Okay. So how many scales per octave? By the way, this is an octave, and this is another octave, another octave. So that each resolution change is called an octave. So how many scales should we have in an octave? They did some experiments. They say that let's run experiments on 8 levels, 7 levels. It looks like 3 levels, 3 scale levels, okay, are enough because this the repeatability, okay, and the matching and kind of peaks out at this level. That's good. So I don't have to run all the other Gausses. So that will be 3 levels per octave. That's good. How about the values of the sigma 0 and sigma 1 and sigma 2? As the initial value of sigma, it looks like 1.6 is good enough. I am going to choose 1.6. How about the other sigmas when I apply it to this one? So this is the initial sigma, and this is the formula for the next one. 2 to the power 2 over s times sigma 0. S is the level number. Okay, so the sigma 0 will be 1.6, and I am going to calculate the other sigmas like that, and that will be it. So that will be the key point localization. I found my key point. I know its location. I know its scale. Previously in the Harris corner detector, I only had the location, not the scale and rotation. I had the rotation and the location, not the scale. Now I have the scale, I have the location, okay. Ratio of the principal curvatures are the, again, that lambda 1, lambda 2 thing, and the rotation matrix, okay. And that will be the key point localization. We might have again some responses from the edges, and using our Harris corner detector technique, we are going to say that okay, eliminate these edges. We are going to take only the corners. So in a way, SIFT corner detection makes sure that whatever it finds is not an edge. Okay, it says that I am going to return only the corners. And for the corners, you remember this lambda 1 times lambda 2 minus alpha times lambda plus lambda 1 plus lambda 2 thing. It is using a different formula. Okay, again, this is lambda 1 times lambda 2, and this one is that. It is taking the ratio of it. This is another method actually. It looks like I won't be able to finish this up, but maybe since I kind of well, I don't want to keep you late. I think I will stop here, and for the next lecture I am going to show you this. I will tell you how to find the orientation of each point, corner point that we find. Orientation assignment I told about you. And then after that, descriptor 128 dimensional descriptor. And after that, I'm going to look at the OpenCV implementation of the alternative key point detectors. SURF is not SIFT, but it is faster. FAST is much faster. BRIEF is much faster, much faster. Then we have the color information and etc. And I will show you how to do that using OpenCV. Okay? And after that, I will start talking about multi-view geometry, multi-view camera geometry, and stereo. Okay, that's it for this week. I'll see you next week.